Here is the trap: the route with fewer roads can still lose. Imagine a delivery app choosing ly shorter road and arriving late because it ignored cost. Shortest path algorithms are built for that moment, when a map has many possible routes and the cheapest answer is not visually obvious. A useful trace starts with A at 0 while every other node waits at infinity until a real route reaches it. The emotional trap is familiar: the route that looks shorter feels correct before the costs are counted. By the end, you should be able to look at a map and decide whether BFS is enough, whether Dijkstra is safe, and why one cheaper-looking route can override another. A path with fewer edges is not always cheaper. Once roads carry costs, the algorithm must compare total distance, not just number of hops. The parent arrow is the breadcrumb trail. Without it, you may know the cost but still not know the actual route. This is how real routing bugs start. Code treats every edge like one step while the product quietly cares about price, time, or risk. When every edge costs 1, BFS expands in perfect distance layers. The first time a node appears, no shorter edge count path can still be hiding. Equal cost edges make distance layers honest: first all 1-hop nodes, then 2-hop nodes, then 3-hop nodes. Keep one tiny map in mind: it connects to B, C, and D. A direct route can look visually shorter, but if its edge cost is large, it loses. The algorithm is not counting road segments, it is adding prices. Each node carries a tentative distance label. It means, this is the best route we have discovered so far, not necessarily the final truth. A tentative label is a best-known offer, not a final truth, until the algorithm has enough evidence to lock it. Relaxing an edge asks a simple question: if A reaches D with cost 2, and D reaches C with cost 1, should C's label improve from infinity to 3? Concrete trace: A has cost 0, D becomes 2, and C improves to 3 through D. That one better offer is relaxation. Pause on the delivery map: is the direct road cheaper, or only visually shorter? The useful feeling here is doubt: has this number earned certainty yet? The frontier is a set of discovered but unsettled nodes. It is not random weighting, it is the edge of what the algorithm currently knows. The parent arrow is the breadcrumb trail. Without it, you may know the cost but still not know the actual route. Dijkstra's key move is to choose the unsettled node with the smallest tentative distance. The priority queue shows the receipt: B has cost 3, D has cost 2, so D locks first. Dijkstra's priority queue is a contest among tentative distances: the smallest safe candidate locks next. Here is the Dijkstra risk card. If all edge weights are nonnegative, traveling farther can never make a locked node cheaper later. If a negative edge appears, early certainty can turn into a lie, so the algorithm needs a different promise. Nonnegative weights protect Dijkstra because extending a path cannot secretly make a locked distance cheaper later. A priority queue is just the waiting room sorted by cheapest current offer. If D has cost 2 and B has cost 3, D leaves the room first. That one rule prevents the algorithm from chasing every possible route equally. A priority queue keeps the smallest tentative distance easy to find. This is where the heap episode becomes useful inside a graph algorithm. The heap does not make the graph smarter, it makes the next smallest tentative distance cheap to retrieve. After locking a node, Dijkstra relaxes the edges leaving it. If D gives C a better offer, C's label changes and its priority queue position changes with it. Concrete trace: A has cost 0, D becomes 2, and C improves to 3 through D. That one better offer is relaxation. Before the next node locks, predict which tentative cost has actually earned trust. The useful feeling here is doubt: has this number earned certainty yet? Distances tell the cost, but parent pointers tell the route. Whenever a better offer wins, remember which node made that offer. In a small map, the direct road can look tempting, but a 2-road route may be cheaper. The algorithm wins by comparing accumulated costs. A settled node is no longer just a guess. It has crossed from candidate into certainty. That vocabulary is the heart of shortest path reasoning. Use the same A to F delivery map. A settled node is a stop whose cheapest arrival time has earned trust, not merely a stop we happen to see. Parent pointers matter because a number alone is not a route. When C improves through D, C's parent becomes D. At the end, you walk those parents backward to recover the actual path, not just the final cost. If no path reaches a node, its distance stays infinity. Infinity is not a big number in the story, it means no discovered route exists. The parent arrow is the breadcrumb trail. Without it, you may know the cost but still not know the actual route. A negative edge can make a route cheaper after a node seemed settled. That destroys the exact safety argument Dijkstra depends on. Nuance: a negative edge does not break every single graph, but it breaks Dijkstra's guarantee because a settled label might become cheaper later. Before the next edge fires, compare the two tentative distances and predict which route gets overridden. This is a good moment to mistrust certainty. A single negative edge can turn yesterday's safe answer into today's bug. Bellman-Ford does not lock nodes early. It repeatedly relaxes all edges, which is slower but can handle negative edges and detect negative cycles. If a cycle keeps reducing cost, there is no stable shortest path. You can loop again and again and make the route cheaper without limit. For Dijkstra, the cost depends on the graph storage and priority queue. The practical lesson is that edges and frontier operations both matter. The parent arrow is the breadcrumb trail. Without it, you may know the cost but still not know the actual route. From one start node, shortest paths to many destinations form a tree of parent pointers, as long as each destination has one chosen best predecessor. A game grid or maze is also a graph. Cells are nodes, legal moves are edges, and movement cost tells us whether BFS or Dijkstra fits. This is a checkpoint. If a negative edge appears, should the algorithm still lock early or become more patient? The useful feeling here is doubt. Has this number earned certainty yet? A* adds a heuristic guess toward the goal. It is not a replacement for the shortest path idea, it is a smarter way to prioritize the frontier. Bellman-Ford feels slower because it refuses early confidence. It repeatedly lets every edge make an offer. That patience is exactly what makes it survive negative edges that would fool Dijkstra. In weighted graphs, marking a node final too early can lock in a bad distance. The timing of certainty is the whole algorithm. Beginner bug: if you mark a weighted node final when it is merely discovered, you can lock in the wrong distance. Most shortest path bugs are timing bugs. The program decides too early that a guess has become truth. Ask: are edges weighted? Are any weights negative? Do I need one destination or all destinations? And can a heuristic safely guide the search? The checklist chooses the tool from the edge rules, equal costs, non-negative weights, negative edges, or heuristic guidance. Start at A with distance 0. Relax its roads. Pick the smallest candidate. Lock it. Relax again. Certainty grows one settled node at a time. Prediction beat: before the next relaxation, ask which label will change. If the viewer can predict that, Dijkstra has stopped feeling like magic. The useful feeling here is doubt: has this number earned certainty yet? A distance number is only half the answer. The parent pointer says which road created that better offer, so the final route can be rebuilt backward from destination to source. Ask the tool question out loud: equal cost, non-negative cost, negative cost, or heuristic guidance. The useful feeling here is doubt: has this number earned certainty yet? If every edge has the same cost, BFS is enough. If weights are non-negative, Dijkstra fits. If negative edges enter, the promise changes and Bellman-Ford style relaxation becomes safer. Shortest path algorithms are not guessing routes. They are managing promises, tentative labels, better offers, settled certainty, and parent pointers that reconstruct the final route. BFS solves equal cost maps. Dijkstra solves non-negative weighted maps by locking the nearest candidate. Relaxation improves offers. Negative edges require a different algorithm. Next, we will study dynamic programming, where the map is not physical roads but repeated subproblems